Alright, in this project we're going to continue our one-dimensional motion, actually two-dimensional motion mini project that we had in an earlier lectures in the loop. I'm going to show you how you can animate the motion itself, then we're going to recalculate the motion for different velocities, and later when we get to nested loops I will show you how to visualize all of these motions. Now, the first thing that you need to do to animate your plot is to move your plot function inside your loop. So we are going to move the plot in the loop. Second, instead of plotting directly x and y, you need to plot x of I and y of I, because here we are trying to plot lines which currently do not exist. Instead, we want to plot each of the points as they become available. So x of I and y of I. Now, if I run this, we are not going to see anything. We're not seeing anything because we are trying to plot only single points. And we don't see anything because we have not specified a marker. So we need to specify a marker for our points. These are not lines, these are points. So let's make it with red circles. So red circles. Let's run it. And as you can see, we actually get only one single point, and this is the last point of our plot. The way to actually animate this is to use the pause function. If we use the pause function after the plot or before the plot, it doesn't really matter. And let's say that we want to pause for 0.2 seconds. And if we run it, as you can see, we are getting different points at different coordinates, and they are just moving up and down, up and down. And at some point this will end. There it is, it ended. So as you can see, the first issue at hand that we have is that we don't actually get our full plot. Instead, each new point gets replotted and the entire plot is recreated with every iteration of the loop. The way to fix this is to use the hold on function. That will hold the plot and make each of our next plots or points be plotted on the same plot. So let's include hold on right after our plot. So hold on, let's run it again, and as you can see, we are now getting a better picture of what exactly is going on. We can see all of our points. We have a couple of issues, but before we get to the issues, a better approach is to not have the hold on inside your loop, because why would you want to run the hold on function 46 times? You need to run it only once. So what we can do instead is to create a dummy plot. This will be the plot to which we will apply all of our stylings before we actually start plotting. So here I'm just going to say plot 0, 0, and I'm going to say hold on. Basically, this will be a dummy plot that will not have anything on it. Its simple purpose is to create the plot and activate the hold on. So delete the hold on from the loop, run it again, and we get the same result. As you can see, the issue that now we have is that the plot itself gets resized all the time. That is because we don't have defined axis limits. So let's define axis limits. As we can see that we start from 0 on the x and we end at 45, and our y is -10 to 25. So here we can say x limit 0 to 25, was it? And y lim is lim -10 to 20. I really don't remember. Let's see. Oops, we're missing something here. And let's move our grids up here as well. Let's run it. Alright, looks a bit better, but these are not the correct limits. So let's find what are our correct limits. Let's remove the plotting, calculate everything, and now find the minimum and the maximum of x. So min of x, max of x is 45, so this will be 45, and max of y 20.4, so let's make it 25. Let's try again. Alright, looks a bit better. There we have it. Alright, we are going to see now our full plot. The plot itself doesn't get resized, and there we have it. I also want to make my plot start at the ground level, which is the 0, and it does start at the ground level, but it doesn't end at the ground level, it ends underground. Let's say that our y equals to 0, this line right here is our ground, and we don't want to go underground. We want to end right here. When we reach this point, we want to stop plotting. The way to do this is to simply find the roots of that equation, because we end here when y is equal to 0. So we have two cases in which y is equal to 0, or here it's actually a bit close, it's close to 0, it's not actually 0, but it's close to 0. And this is where we want to end. So we simply need to find the roots of our y equation. To do this, we're going to use the roots function. So we have to find y roots, let's do it down here. Y roots is equal to roots of something. Now what is this something? This is our equation for the y. So we have three different coefficients. We have t to the second power, we have t to the first power, and we don't have any t. So we need to specify this in the opposite order inside our roots equation. So we need to use the following equation. We need the acceleration divided by 2 multiplied by t squared plus v times t to the first power plus x times t to the 0th power. So if you remember from one of our earliest lectures, in order to find the roots of that equation inside our roots function, we don't have to use the t, we only need to specify the coefficients. And to do this, we're going to say a of y, which is the acceleration, divided by 2. This is our first coefficient, this one. Then we need the next one, so comma, we need only the velocity, vy, and we don't have initial starting point, or rather our initial starting point is 0, so here our coefficient is 0 times t to the 0th power, so 0. These are the three coefficients of this equation, this one right here. These are our three coefficients. If we run this function, these are our four roots, the roots at which we get y equals 0. So we are going to switch things a bit, and we are going to take the non-zero root from these roots. So let's save it in a variable y roots, and we are going to take the non-zero roots. So non-zero, let's see if it's going to work, and then we will apply it to the script. So y roots that are not 0, like that. We are going to use logical selection, but we are going to use the not equals operator. As you can see, we have only two roots, one is 0, the other is not. We don't care what is the value of the other root, as long as it's not a 0. And if we run this, we get the non-zero root. So here we're going to save it. Non-zero root is equal to y roots of y roots that are not equal to 0. Like that. Now, how are we going to use this? We're going to use the non-zero root to generate our vectors. Now we're not going to generate our t vector up here. We're going to generate it down here, and that goes for the x and y as well, because they're dependent on the t. So I'm going to move all of them down here, and we're going to generate it with the linspace function. So linspace from 0 to the non-zero root, and we want a specific number of points. So let's say that we want 50 points. 50 equally distributed points between the 0 and the other root, which will give us y equals to 0. If we do this, let's use it first. You can see that we get 50 points which are between 0 and our non-zero root. So we get equally distributed values between our two roots. If we run our code now, let's see if it's going to work. We should start at y equals 0, and we should end somewhere around here at y also equals 0. Let's see. And there we have it. So if we increase the time, this way we're limiting the time basically. We're basically calculating which second the rock is going to hit the 0 again. So as you can see, we are not even going below the 0 anymore like we did with the previous way. We are specifically on the 0. We start at the 0 and we end at the 0. So these are the basics of animating your plot, making it a bit more dynamic, a bit more flexible, but we have a lot more work to do, and we're going to make this code work for more than one single velocity. This means that we have to use loops in a couple of other places. So let's go ahead and do this.